48可以50就不能。对，终于哇，真的是久，太久了，5点10多分。啊！Seriously. Was it always like this? Hold up. Yeah. Okay. So I'm just gonna start today's lesson. Not lesson, like what is it? Vlogging? Vlogging about the lesson? Yeah. There we
Welcome. We're here today to dive into the world of medium voltage switchgear. Specifically, we'll look at 3 main types: metal clad, metal enclosed, and metal enclosed gas insulated switchgear, or MEGIS. In this video, we'll explore each type's design, application, and features, as well as key industry standards to help you pick the right equipment for safe and effective operation. But first, what exactly is medium voltage switchgear? Medium voltage switchgear is a centralized collection of circuit breakers over time.
Also, when events occur, fuses are designed to blow, which means they must be replaced, leading to potential cost in maintenance and downtime. With circuit breakers, you have different benefits. Circuit breakers are designed to be resettable if an overload event occurs. They also can have more modes of protection, including ground fault and arc flash protection through electronic trip units or protective relays. Trip units and protective relays also allow for highly customizable protection settings, allowing for more adjustable coordination with downstream equipment. A circuit breaker provides 3-phase protection and will trip all 3 phases if an event occurs. They can also provide increased visibility and control through communications. However, with a circuit breaker, you're going to have higher initial cost and maintenance requirements due to mechanical complexity. As your interrupting rating requirements increase, circuit breakers may not be able to achieve desired ratings or may be cost prohibitive. In summary, the benefits of metal enclosed switchgear include lower cost, ease of access for maintenance as compartments are more open, and flexible design due to less strict design standards. Metal enclosed switchgear is ideal for applications with lower fault current ratings, cost or footprint constraints.
I think the biggest problem is that people don't really understand what metal enclosed switchgear is. Like there's a saying in Buddhism, not a saying but like a phenomenon very frequently in the ancient Buddhism texts, where it's like you like comparing something, for example, to like a chariot. It's like a practical transportation or tool to like make the doctrine or the manual easy to understand. I think that's the problem with, at least this kind of like deeper type of information within the manuals, or like deeper type of information.
And when lower switching operations are needed.
Metal Metal-clad switchgear is the most common design of switchgear used for the distribution of electricity throughout a facility. Driven by the IEEE C37.20.2 standard, metal-clad switchgear is a heavily compartmentalized design that includes multiple features to enhance operator safety. Each component, such as circuit breakers, instrument transformers, cables, and bus bars, are housed in individual grounded metal compartments. The standard requires that no live parts are accessible. This includes features such as automatic shutters on removable draw-out compartments, which offers safety benefits by isolating live parts to help prevent accidental contact by an operator. Low voltage or secondary control devices and associated wiring are also isolated from the medium voltage or primary circuits by grounded metal barriers, but can be mounted on doors in front of the circuit breaker or other devices. The IEEE C37.20.2 standard requires that the switching and interrupting device must be a removable type with a mechanism between connected and disconnected position, and equipped with self-aligning, self-coupling, primary and secondary connections. In metal-clad switchgear, a vacuum circuit breaker is used as this interrupting device. In a vacuum circuit breaker, the arc interruption takes place inside of sealed vacuum bottles. The contacts inside the vacuum allow the arc to be extinguished quickly, reducing the arc energy in a very compact space. The breaker requires a protective relay to act as the brains or trip unit for this device. The relay will take inputs from current and voltage transformers installed in the equipment to interrupt fault conditions and monitor the equipment's performance. Breakers and auxiliary devices such as voltage transformers must be mounted on a removable draw-out mechanism, which allows for easier maintenance and a visual means of disconnect. For a complete insulation system, the medium voltage bus is coated with epoxy insulation throughout. Bolted joints and connections are covered by removable silicone insulating boots. Lug connections also need to be insulated. Those can be field taped or cable boots can be purchased from the manufacturer. Mechanical interlocks are required for proper operating sequence. As an example, an interlock is integrated in the racking screw housing to prevent racking of the circuit breaker while closed. Metal-clad is known for its robust construction, but also provides application-specific benefits, such as automatic transfer schemes and increased control, since electrically operated breakers are used as a standard. In summary, the benefits of metal-clad switchgear designs include enhanced safety through fully insulated bus bars, isolation shutters, and compartmentalization, high reliability with superior fault isolation and with mechanical interlocks that prevent unintended operation, and a robust design allowing for a variety of configurations. Metal-clad switchgear is ideal for applications where an extra level of protection and reliability are required.
Compact switchgear, also known as metal enclosed gas insulated switchgear or MEGAS, is designed to reduce the footprint of a lineup, especially at the 27 and 38 kV classes. These configurations are built to the IEEE C37.20.9 standard. The construction of MEGAS equipment is a vacuum interrupter or breaker in a sealed pressurized tank. The overcurrent protection is provided by a vacuum interrupter in conjunction with a protective relay, similar to metal-clad switchgear. The gas medium in the tanks acts as an insulator due to its high dielectric strength, allowing for a reduced footprint as compared to air-insulated switchgear. With the main
Managing and growing your ISO program is a journey, and there's two ways to travel.
With the main power components installed in a hermetically sealed tanks, there is no maintenance required and a reduced likelihood of arc faults, preventing downtime of the equipment. The tank is designed as a sealed pressure system with a maximum leakage rate of 0.1% per year by the standard. With the design, it is ideal for high altitude installations, as derating is not required as it would be for air insulated applications. The MEGAS standard enables increased BIL options for higher voltage classes. For example, the MEGAS standard for 38 kV provides the option to have a 200 kV BIL system, where metal-clad switchgear standard is only 150 kV BIL. This will allow you to connect to a utility with 200 kV BIL requirements. Unlike metal-clad switchgear, which utilize draw-out breakers to isolate the circuit, MEGAS uses a 3-position switch to connect or disconnect the breaker from the main bus. The final position in the 3-position switch allows you to ground the connected line or load cables through the closed circuit breaker. To safely access the cable compartment, interlocking is required with the main breaker to prevent an operator from entering the cable compartment while the breaker is in the closed position. In summary, the benefits of compact switchgear or MEGAS include higher system uptime with no maintenance requirements, reduced footprint due to the compact design making it suitable for application with space constraints, and a safe alternative for isolation and grounding using the 3-position switch. Compact switchgear is ideal for space-limited applications, especially in higher voltage classes, and provides excellent performance in harsh environments. Now that we've covered the 3 categories of medium voltage switchgear, let's discuss specialty applications. An important safety feature for medium voltage switchgear is the arc-resistant design option. Conventional electrical switchgear built to IEEE standard provides a relatively safe environment for equipment and maintenance personnel during normal operating conditions. However, conventional switchgear is not designed to withstand the enormous energy released during an electrical fault condition. Switchgear certified as arc resistant is designed to safely contain and redirect arc flash energy away from the operator. This is typically accomplished by diverting arc flash energy through a plenum to an area it can be released without danger of harm to personnel or equipment. In addition to various IEEE design standards for medium voltage switchgear, arc-resistant gear must comply to the testing requirements designed by IEEE C37.20.7. The most common arc-resistant design is Type 2B. Type 2B must keep the operator safe on any side of the equipment during an arc event with the low voltage compartment door open.
In recent years, digital advancements are also helping transform switchgear to significantly reduce downtime, lower maintenance costs, and get operators away from the equipment. By incorporating relays, voltage and current sensing, and communication capabilities, you collect vast data on power quality, equipment performance, and event history, as well as provide control functionality from safely outside the arc flash boundary. This data can be sent to a central monitoring system for real-time analysis, optimizing efficiency and predictive maintenance. Examples of technology helping optimize switchgear operations include 1. Arc flash relays. These devices use light sensors to detect an arc flash to open a breaker faster, reducing the duration and impact of the event. 2. Thermal monitoring. Continuous thermal sensors check lug connections and monitor potential hotspots, providing real-time trend data on system performance. The system provides maintenance alerts, allowing the operator to be proactive instead of reactive. This can eliminate the costs and maintenance associated with periodic IR scans. 3. Remote racking. This feature can be used to perform operations such as disconnect, test, and connect of circuit breakers and auxiliary compartments of switchgear to increase operator safety by keeping them outside of the arc flash boundary. 4. Partial discharge monitoring. This solution helps detect corona due to insulation degradation, allowing operators to address issues before they become catastrophic.
From flexible metal enclosed designs to robust metal clad solutions to highly compact MEGAS options, we hope this video helped you better understand medium voltage switchgear. But always remember when installing switchgear, careful planning is crucial. Considerations for transportation, site dimensions, and environmental hazards will go a long way to ensure a long, safe, and reliable equipment lifespan. To learn more about how to correctly specify and install medium voltage switchgear, please visit us at eaton.com/mvswitchgear. To see medium voltage equipment in action, Contact us or your local Eaton representative to schedule a visit to one of Eaton's Power System Experience Centers today.
And this thing up again. Oh, finally. Jeez.
A protective relay is a critical device in electrical systems. Its job is to detect abnormal or dangerous conditions, like faults, within the power system and then act quickly to clear the fault from the system. Using input from current and voltage transformers, a protective relay monitors system characteristics that may include current, voltage, frequency, and phase angle. When power system conditions exceed set threshold limits, the relay sends a signal to the circuit breaker trip coil to trip the breaker, isolating the fault from the rest of the system. Unlike low voltage breakers, most medium voltage circuit breakers do not have trip units. Medium voltage breakers rely on external components to tell them when to operate. Think of the external components, perhaps a breaker control switch or a protective relay, as the brains of the operation, with the breaker itself being the brawn of the operation that makes it happen. There are two different types of protective relays: electromechanical relays and microprocessor-based digital relays. Digital protective relays are the predominant modern solution. However, you will find that many electromechanical relays are still in use today. An electromechanical protective relay uses the magnetic field produced by an electromagnetic coil to close a contact, initiating a breaker trip. For example, a time delay overcurrent relay is made up of a rotating disc with one side of an electrical contact held in place by a spring. Current passing through the relay produces torque that rotates the disc. When the current, and therefore the torque, is great enough, the disc will rotate such that the moving electrical contact on the disc touches a stationary contact, triggering breaker operation. The current level required to trip and the time to trip are specific to the power system in which the relay is applied, and is set by positioning screws or pins at the front of the relay. An electromagnetic relay can only perform one protective function, serving only one phase of power. In the example I just described, one electromechanical relay would provide time delay overcurrent protection for one phase of the power system. To provide complete protection to all three phases, two additional relays would be needed for a total of three. If additional protective functions are required, additional relays would be needed. We'll talk more about protective functions momentarily. Initially developed in the 1970s, microprocessor-based digital relays are the modern protective relay solution. Instead of using mechanical components and magnetic fields, multifunction digital relays use programmable logic to set value thresholds. Unlike electromechanical relays, digital protective relays are multifunctional. They have the capability of offering protection for multiple functions to all three phases of the power system simultaneously. Each individual function performed by a relay has a corresponding number code set by ANSI IEEE standard C37.2. The parameters of each function are set for the specific installation based on the results of a power system study. Current transformers external to the protective relay are required for current-based functions, and voltage transformers external to the protective relay are required for voltage-based functions. Common protective relay functions include number 50, instantaneous overcurrent. The instantaneous overcurrent function sends a trip signal anytime current measured by the current transformers exceeds a set value. This function does not introduce any intentional time delay. Number 51.
Did you get it? Mark, we're barely making it this month. The car payment is late. The mortgage is due next week.
I know. I don't know what else to do.
1. Time delay overcurrent. The time delay overcurrent function sends a time-delayed trip signal based on the magnitude of measured current according to pre-programmed time delay curves available within the relay. Remember our electromechanical example? That was a 51 function, time delay overcurrent. Number 27, undervoltage. The undervoltage function sends a trip signal when the measured voltage on the system drops below a set value. Undervoltage protection is important in protecting electromechanical devices like pumps and motors, as undervoltage conditions draw higher currents, which can damage devices and reduce overall lifespan. Number 59, overvoltage. The overvoltage function sends a trip signal when the measured voltage exceeds a set value. Number 87, differential. Differential protection compares measured current in different locations. For example, bus differential protection compares the current flowing into a bus to the current leaving the bus. During normal operating conditions, the sum of these currents should be 0. During a fault condition, the sum would no longer be 0, and the relay sends a trip signal to the breaker. Transformer differential protection is similar in that it compares the current entering a transformer primary to the current leaving the transformer secondary, taking into account the turns ratio. And finally, number 25, synchronization check. The synchronization check, or sync check function, verifies that the voltage, phase angle, frequency, and phase rotation across two sides of a breaker are the same prior to closing the breaker. This is very important for main-tie-main systems with automatic transfer functionality. Each of these functions may also be given a suffix to describe where the function is applied. Common suffixes include P for phase, N for neutral, G for ground, T for transformer, and B for bus. For example, a 59N relay would protect from neutral overvoltage, while a 50G relay would provide ground overcurrent protection. An 87T relay provides differential protection over a transformer. In addition to protective functions, ANSI numbers are also used to describe other devices. For example, 52 is a circuit breaker, and 86 represents lockout, which requires a manual reset after a breaker trips. Digital protective relays offer multiple functions within a single device. The functions included in a relay are selected based on where they will be applied in the power system. Relays are applied to protect overlapping sections of the power system called zones of protection. Using this example of a power system with two incoming lines, a main-tie-main primary substation feeding two transformers, and a secondary substation feeding loads, the following zones of protection would likely be considered. At the top of the single line, an incoming line and primary substation main breaker represent a line zone of protection. Each incoming feed would be its own zone of protection, and each would be protected by its own line protective relay. Moving downstream, the primary substation main and feeder circuit breakers are within a bus zone of.
I think this is the problem, right? It's like there's like if you like this is like more of a philosophical take, right? When you are so focused on this one, you forget the other stuff, right? If you put all your efforts into this thing, you forget to clean or tidy up. You have less time. Not necessarily you cannot, but like you have less time to make sure you can tidy up your pillow or get some good sleep. I think that's also like the bigger things of why, you know, when you make these videos, it's kind of difficult. How much use is this? It's not that much.
Protection. This zone covers the primary substation main breakers, the primary substation bus, and all of the primary substation feeder breakers using bus differential protection 87B. Next downstream is the transformer zone of protection, which uses a transformer protection relay and includes the associated primary substation feeder breaker, transformer, and secondary substation main breaker. This zone of protection would use a transformer differential relay 87T. Then, the secondary substation main and feeder circuit breakers are protected by a bus zone of protection, similar to the primary substation. And finally, the feeder breakers and loads are protected by individual feeder zones of protection using feeder protection relays. Each feeder protection relay includes instantaneous and time delay overcurrent and may include additional functions like overvoltage, undervoltage, and others. Notice that the zones of protection overlap. This overlap is intentional to avoid leaving any area unprotected. Additionally, two levels of protection are provided within the overlap zones. A fault in an overlapping area would be able to be cleared by either of the applicable protective methods, resulting in primary and backup protection. Understanding of protective relays is critical to understanding medium voltage power systems. For more information, visit eaton.com, and to see some of these protective relays in action, contact us or your local Eaton representative to visit one of Eaton's Power Systems Experience Centers today.
Is it done? Yeah, it's done. Okay, this is the end of today's video. Thank you very much. Goodbye.